In the previous lecture, we had worked out an example on homogeneous transforms. And in the process of explaining the homogeneous transform, while doing the example, we had also discussed how the cross product is represented in the matrix form. And so we had constructed the A cross matrix, which was a skew symmetric matrix. Its property is that its transpose is its negative. So the diagonal terms are zero and the off diagonal terms are just skew symmetric. So if you have minus AZ here, you have AZ here, AY here, then you have minus AY here, minus AX, you have AX here. So this was the property of the A cross matrix. And we could also see that this cross product A cross B could also be written as minus B cross A. So we will get the same vector even if we take this as minus B cross and this as A vector. So that was a discussion in our last lecture. Then we proceeded with constructing uh, the homogeneous transform for a little more complicated case, and we completed that example. In today's example, we will proceed a little further. We'll see what we can actually do with the homogeneous transform. I have taken some boxes which I have prepared beforehand, and I'm going to make use of them. So let's say that we take this box, and in fact we could take, yeah, let's take this box and I'll just construct a reference frame. So we have a frame here, and let's say this frame, we have the origin of this frame here. We'll say that this frame is O0. This frame is frame 0. So this view, let's take it as a simple example. So this we could take as the x-axis corresponding to the frame 0, and this corresponding to the y-axis of the frame 0. And here we can have the z-axis as if it is coming out of the plane of, so we can represent it using a circle dot combination, a small circle. So we just have, oh sorry, it's got in red. We just need a small circle here and a dot. So this becomes the z-axis, as if this z-axis is coming out of the plane. So this is our z-axis, z0. Now we can also have another reference frame. Let's say the frame in red, which we have already constructed here. Let's take both of them. And we'll place it over here initially. So it coincides. Okay. Here, The frame in red, I've only shown lesser number of boxes here. But this frame, let's say that um, it's frame 1. So this is the frame 1, and um, this is the x-axis of the frame 1 and the y-axis of the frame 1. Right now, the directions are coinciding. So we have the z-axis of frame 1 coming outside, so coming out of the plane, and this is the origin of frame 1 as well. Here we had the origin of frame 0. Okay. Now let us try to rotate this frame. We'll rotate this. Sorry. Let us, or rather, let us take point, a point on this frame. Uh, Let us take a point, say, could take any point. In fact, let's to make it simple, let us take just a simple point, which is located here, so indicating it in this manner, and the vector that is representing the position of this point. If we call this point as P, then the vector representing the position of this point in the frame 0 would be this vector here. From here to here. And this vector, if we write it in terms of its components, we can represent it as the position of the point P as observed from the origin either of frame 0 or 1, and we could also say expressed in 0 or 1, and this is equal to we have 2 units along the x-axis, no units along y, no units along z. So this will just be 2, 0, 0. So this is the vector. Yes. Now suppose we operate a transform, a homogeneous transform on this, which is just uh, let's say it's equivalent to just shifting the frame. So if we just take this transform, we consider it as if this frame is shifted. So we'll move this frame. Let's say we'll just move this frame by 1 block. Just to give you an idea, just shift this frame by 1 block to the right. So now what has happened? is this origin has shifted, all this paraphernalia has shifted here. Okay. Yeah. Now, if we are to look at the position of the point P in the red frame, what is the position of the point P? So you will see that the position of the point P, the same point P, as observed from the origin of the frame 1, but uh, and also expressed in terms of the origin of in terms of the frame 1, this will be equal to just one division to the right, that is 1 along the x-axis, 0, 0. Now, what is the relationship between this? How do we get this? It's easy to see. Now, suppose uh, we take this transform, we take the homogeneous transform, uh, we take this homogeneous transform, but before that, let's write down this vector R. So we'll keep this as 1, 0, 0, 1. And here we will construct our T matrix. Okay. So this T matrix, um, just have this box here. And we know that the components of this T matrix will be 0, 0, 0, 1. And if you see the orientation of the frame 1 with respect to frame 0, you will see that the unit vectors of frame 1 are also parallel to the unit vectors of frame 0. So here you will have the same thing. So this will be 1, 0, 0. This will be 0, 1, 0 and 0, 0, 1. So as far as the orientation is concerned, that is this part of the transformation matrix, you see that it remains unaffected. It's just a unit matrix. Okay. The second part is what is the location of the origin of the frame 1 with respect to frame 0 as seen by the person standing in frame 0. So here he sees that the origin is located at a unit of 1 along the x-axis, and here it is 0. Okay. So here we have the T matrix locating from frame 1 to frame 0, and here we have the position of the point P observed and expressed in the frame 1. We also have augmented it with the 1 below. Okay. So this vector here When it is operated on by this transformation matrix, what do we get? We get 1 into 1 plus 0 plus 0 plus 1 into 1. So 1 plus 1, that is 2. Here we get 0, 0, 0, 0. Here we get 0, 0, 0, 0. And here 1. So you can see that this is exactly what we can also see in the diagram. We can see that this represents the position of the same point P as observed and expressed in the frame 0, and this part is augmented by with 1. So here we have the T matrix, is a 4 by 4, and you know how to construct this T matrix now. So we have the position of the same point expressed here and written in terms of the frame 1, the position of the same point as observed and expressed in the frame 0 is here, and this is the transformation relating the two. Now you can look at this transformation in two ways. What are those two ways? If you just consider the position of this point, so if you are just looking at it as if you have a vector in the frame, if you have a vector in the frame 1, okay, and you want to just if you have a point in the frame 1 and you just want to translate the point along the x direction by an amount of 1, so you just have to operate on it by this, keeping the orientation unchanged. You can see this unit matrix represents an unchanged orientation. So the orientation of frame 1 and frame 0 is the same. Can all of you hear me? Please respond.
Yes, sir.
Yes, sir.
I hope you are following this lecture. I'm going a little in a very simple manner so that you follow it. Now, the point is that you have got this, you got the location of the point P, and you started with the red frame, let us say. Okay, you know it as 1, 0, 0, 1. Now, if you just want this point P to be translated 1 unit to the right, you can do that. Okay, without considering this, if you just look at it from this point, that initially so the first way in which you can see this is you can consider as if the point P, this point P, which was lying here at a location of 1, 0, 0. Okay, you can view it in this manner. Has now been translated. It has been shifted right by 1 unit. And how did you get that shift? You just shifted by placing this, shifting the origin by 1 unit to the right, 1 unit along the x-axis, keeping the y and z unchanged. Okay, So you are able to move from point P here to a point P here. Let us say this corresponds to P, P initially. Let's say this corresponds to, let's say it corresponds to Q. So you are able to get this shift from P to Q by just operating on this uh, vector representing this position. By just operating on this, it could be shifted. You ensure that the origin of the frame 1 with respect to 0 was specified here. Okay, so this homogeneous transformation, it can serve the purpose of translating the points. Okay, so you can just translate vectors. When we say translate, we mean a movement, a shift without changing the orientation. Okay, so suppose if I want to change the um, if I want to move this, the location of the point P from here, I wish to place it here. Okay, or here. Let's say here, for example. How much should I shift it? I have to shift it by. Can you tell me how much we have to shift it?
1 unit horizontal, 2 unit vertical.
Yes. So we have to shift it just. Um, uh, so from here, we just want to shift it here. So the transformation that is needed for this, can you tell me what will be the transformation?
In
One two
x-axis
zero.
1 unit and
Let's
y-axis
say
2 units.
P is the same. Okay. So P is 1, 0, 0, 1. Okay. Here also you will have, so this is the P. This is the position of the point P. Now I'm not writing it in terms of, let's say we have everything in terms of frame 0 only. I'm not shown any red frame here. But I want to shift it from here to here. So I can treat it as if I'm shifting the frame itself. Okay. So how do we do that? We just bring in so if we take this as, this will be unchanged. So 1, 0, 0, 0, and here this will be 0, 1, 0, 0, it will be 0, 0, 0. Here. So here, what is the vector that you will place here? 3 by 1.
1 2 0.
1, 2, 0. So the shift will be 1 to 0. If you do this matrix multiplication, what will you get? If you do this matrix multiplication, so this is going to be the transformation from, it's just a transformation. I'm just going to write it using a T matrix only, not.
Sir,
Yes.
sir, P is also shifted 1 unit before.
Yeah, that's right. No, now I'm taking another example. Instead of that, I want to shift the point over here.
Yes, sir.
Yeah, is it okay?
Yes, sir.
So it becomes 1 plus 0 plus 0 plus 1. That is 1 plus 1, that is 2. Then you have 0 plus 0 plus 2. So again you have 2. Then you have 0 plus 0 plus 0 plus 0. And finally this will be 1. So you can see that this represents a shift. You have been able to shift the location of this point. Got it? By how much amount? By the amount which you specified here, 1, 2, 0. You wanted to shift the location of the point 1 unit to the right and 2 units above. So you shifted it in the corresponding direction. So what this homogeneous transformation can do is it can translate vectors. Got it? So it can translate the position of points. Okay? So if you had Q, even that would have got translated. You have P, that also will get translated. Okay. So in this, suppose you started with both points P and Q. You had these 2 points and you operated with this. So P would have given you this one and Q will give you, Q will be shifted over here because it's the same translation. So Q will come here. Got it? So P will come to this location P dash, Q will come to this location Q dash. And how have you achieved it? By operating the respective position vectors of these points with this transformation. So the transformation matrix can be used to translate the location of these points. Okay, it can use to translate. So the vector PQ has got translated to P dash Q dash over here. Is it clear? So this is one thing. Of course, you could take vectors in other orientations also. They will give the same result. Over here, I have just taken so that it's very simple. So if you would have taken some other vector, let us say, if you were to take a vector, say from here to here, okay, say we call this as H and this as L. Okay, you can shift the vector HL to another location. How can you do that? You will have to translate the location of the point H here. You have to translate the location of the point L here, and that can be done using a transformation matrix. So how do we do that? So you will have to write down the orientation of the position vector of the point H and L, and then you'll have to operate those position vectors with the transformation matrix. And what will be the transformation matrix? Since there is going to be no change in the orientation, this part will remain the same. And the transformation, the translation will be performed by the amount to which you wish to shift the origin. Say, for example, in this particular example, if we wish to translate this vector from here, from HL, we just wish to bring it to here, this location. Oh, I'm sorry. Let's shift it here. Okay, so now we have got the new location as H dash L dash. Okay, and how did you do this transformation? You shifted H, the location of this point here, and you shifted the location of this point here. And how was that done? It was done simply by operating on it, you see the orientation of this line has not changed. The length of this line has not changed. What has changed? Just it has just translated from here to here. Got it? So the transformation that would be required in this case, the transformation that would be required in this case would be what? Can you let me know? In fact, we could just take this part itself and just modify it. If I wish to move this line from here to here, so I'll have to shift H to H dash and L to L dash. So what is the transformation that will do that? Can you just tell me? It's a simple translation. So this unit weight matrix R will remain the same. What will change are the elements here. Okay. So along the x direction, how much do we wish to go?
-1.
-1, -1.
-1. Along the y direction?
+1.
Along the y direction? Also +1.
+1.
+1. Okay. So now if you operate 1001, so if you operate this on this, what will you get? You will get the location of H dash. Okay, you can straight away write H dash as what? 1 into 1 as 1 plus 0 plus 0 into 0 plus -1 into 1. So what do you get? Yes, you get 1 minus 1, that is 0. So you can see the x coordinate is 0. X
0 1 0
coordinate
1.
of h dash is 0. Then yeah, so you'll get here 0 plus 0 plus 0 plus 1. So here you will get 1. Okay, and you can see that the y coordinate of h dash is indeed 1. Here when you multiply 0 0 0 0, so here you will get 0 and here you will have 1. So the position vector for h dash, okay, this position vector for h dash, it changes. Now here we are assuming that the frame was the same frame, okay, but the points, the position of the points got translated. The vector got translated. Got it? So the transformation matrix can be viewed in this way as well, that it can be used to translate vectors. I hope this point is clear to you. So this is one way of looking at the transformation matrix. The second way, of course, is well known to you. It indicates the location of one frame with respect to the other. So we can use the transformation matrix for two ways. One is to translate vectors, and secondly also to specify the uh, the position or the location of one frame with respect to another frame. Okay, so it can be viewed in two distinct ways. Now let us look at it. Here we had done a pure translation, and because we had done a pure translation, you see this matrix was a unit matrix. Now let us perform a pure rotation. We will keep the translational part as 0, but we'll perform a pure rotation and see what happens. So again, we have two distinct possibilities. I think we can make use of some of these diagrams. So I'll make use of this. I'll just copy it. Let us erase this part.
Sir,
Yes, please go
sir,
ahead.
sir, can we also increase the size of the length HL if we want to just magnify it two uh, by a magnification factor of 2 and 3? This can
You can do that. You
We
can
can
do that.
modify
But we are
scale.
not. Yeah, we are not discussing that. That's used in computer graphics. Okay, so we'll have to have a magnification in that. That can be done. That can be done.
okay, sir.
Okay, I mean, let's not get into that at this moment because we are right now trying to apply it to our robotic systems where the magnification is not going to change as far as these positions are concerned. That's more important for us in computer graphics, the issue which you have raised. Okay,
Yes, sir.
yeah, but it can be done. You are right. It can be done. So now let us see from let us perform a rotation. For the rotation, I think to start with, I think we can erase this totally. We'll keep this part as it is. Yeah. Here now I'm going to shift this back, this red frame back here, and we are going to now we plan to rotate this one. Okay, so we'll tilt it a little. Maybe we can tilt it by some angle which we know preferably. Or if you want a standard angle, you could do it by 45 degrees if you want, but then 45, okay, let's do it by 45 degrees. Let's see what happens if we place it here like this. It's almost 45 degrees. Yeah. So if we look at it, here we have the point P. And let's take this point as P dash. What we are doing in this transformation is going from P to P dash. Okay. This point here gets rotated and it comes here, it comes here, it comes. Now, how does this happen? So, the orientation has taken place by the amount of theta. In this case, we know that it is 45 degrees, but in general, let's say it is theta. So, this angle which we have is theta. Okay. So, how are we going to get this particular rotation? So if we look at it from the transformation point of view, we already have the position vector of the point P. We can erase this. Second part here. I'll also shift this a bit. So if we write this in terms of the frame 1, in the frame 1, it still continues to be 2, 0, 0. Okay. So in the frame 1, the position of the point P, which we write here as P dash, okay, in the frame 1, it is just 2, 0, 0. This is the position vector. Got it? Now, what is the relationship between this position vector and between the vector which is shown over here? If we operate, if we take the transformation, we know that if we want to rotate it by angle theta, here we will have to do cos theta. If you look up your notes, you will have to have your sine theta, and here you will have 0, and this part will be 0. Here you will have minus sine theta, here cos theta, here 0, and here 0, and this will be 0, 0, 1, because this about z axis there is no rotation, and this will be 0. And here, because we are not having any translation, so this part will be 0, 0, 0, 1. So there is no translation here, only rotation. It's a case of pure rotation. So we may write this transformation like this. I think I'll have to use a rectangle. Okay, this part is here. This is our transformation matrix. You can see that this part remains unchanged. This part continues to be 0. Okay. So this is our transformation matrix. If we operate this transformation matrix on this vector, what is this vector? It is 2, 0, 0, 1. So it is 2, 0, 0, 1. What are we going to get? We will get 2 cos theta plus 0 plus 0 plus 0. That is 2 cos theta. In this case, 2 cos theta. Here you get 2 sine theta. 2 sine theta. And plus 0 plus 0 plus 0. Here you have 0 plus 0 plus 0 plus 0. So this is 0. It's as expected, z component. And here you will have 1. So this is the location of the point P. If you view it, if you look at the point P in the red frame, sitting on the red frame, you will see it as 2, 0, 0. But if you look at the point P from the frame 0, now P dash from the frame 0, it has a coordinate 2 cos theta, 2 sin theta. Okay. And you can see for yourself that is the case because this is x coordinate will be the adjacent side. Okay. You just draw this. You will have the x coordinate. So this is going to be the projection on the x-axis, and this is going to be the projection along the this is along x-axis. So you have this part as 2 cos theta and this part as 2 sin theta. Okay, so this point P has got shifted here, 2 cos theta, 2 sin theta. What has happened? Suppose you take some other point. If you take this point here, or if you take this point here and you rotate it by the same amount, this point will come somewhere here, right? So in that case, its coordinate will be given by the same transformation matrix operating on this position vector. So you can look at this transformation again in two different ways. One is that it can be used to specify orientation of frame 1 with respect to 0. So you can say that frame 1 is oriented with respect to frame 0 by an angle of theta as if it is rotated about the frame 0, z-axis of frame 0 by an angle of theta. The other way of looking at it is that you can rotate the position vectors of these points by an amount of theta. If you just have one frame and you have the position vector of a particular point, you wish to rotate it. You wish to rotate that vector by that means this vector which was here, it has now come here. So you have rotated it by an angle of theta. Okay, so it can be viewed in two different ways. I hope this point is clear to all of you.
Sir,
Yes.
sir,
Yes,
if
sir.
theta is clockwise or anti-clockwise, then there is no change in the matrix.
Yeah. So in this case, theta, what we have taken is the
Anti-clockwise.
positive direction, counterclockwise.
Counterclockwise
If you
direction.
want to take it clockwise, then it will become minus theta. Okay. Conventionally, we always the angle is measured counterclockwise. I think you have done that in your trigonometry and geometry courses. So we follow the right hand rule, and the angle is measured from the positive direction of the x-axis, keeping your thumb oriented along the positive direction of the z-axis, and the direction of the fingers of the right hand indicate the angle of rotation, right? Any other query? Hello?
No, sir.
No, sir.
In that, we will conclude here for today. I think I'll stop here today. Yeah.